Hello again. In this video we're going to look at something called the conservation of momentum. It's a little different from the conservation of energy we talked about last module. In the conservation of momentum, we can think of it as one of two different ways, either with a formula or with an example. When we first, and actually they are related for that matter. The formula for the conservation of momentum is this: m1v1 equals the opposite of m2v2. And the ones and twos are just subscripts denoting the two different objects. Now, conservation of momentum, think of it as this. Momentum after a collision of the two objects going in opposite direction are the same. So, for instance, recoil in a rifle. If a rifle is firing a bullet, the bullet going through this way has the same momentum as the rifle kicking back this way. Now they have the same momentum. That doesn't mean they have the same velocity. In fact, they have vastly different velocities. A bullet has very, very small mass, but very large velocity going in that direction. The rifle, relatively speaking, has a very large mass, but a very small velocity in the opposite direction. So let's look at an example that will better explain that. Say I gave you that the bullet has a mass of 0.005 kilograms. Rifle has a 0.8 kilogram mass. The bullet's velocity is 800 meters per second, and we want to look at the recoil velocity of the rifle. So we look at the formula for conservation of momentum. The m1v1 equals the opposite of m2v2. So your m1, we'll let the ones be the bullet and the twos be the rifle. So m1 is your 0.005 kilograms times v1, which is 800 meters per second. And we have the opposite of 0.8 kilograms, which is m2, times recoil velocity of the rifle, or v2. So you take your 0.005 times 800, and then we divide it by the negative 0.8 kilograms, because we want to get v sub 2 by itself is being multiplied by this number. The opposite of multiplying by it naturally is to divide by it. So we divide by negative 0.8 kilograms. What you do to one side of the equation, you must do the other, which is how we get here. Punch it in, you get negative 5 meters per second. So let's look at that for a second. In other words, if you have a bullet being fired from a rifle, and the bullet has a 0.005 kilogram mass, but is moving at 800 meters per second, the rifle is kicking back. It has a 0.8 kilogram mass, but it's kicking back at 5 meters per second in the opposite direction of the bullet. Now a meter is about yay tall. 5 meters is going that far in 1 second in your shoulder. That's why hunters or professional shooters or even casual shooters wear padded vests. That way it helps protect your shoulder. Because that's okay once or twice, but after you shoot 100 times, it gets a little sore. So as far as a recap here, the momentum of the objects after the collision going in the opposite directions are the same. In fact, let's check that. If we take 0.005 times 800, we get 4. So basically the momentum of the bullet is 4 kilograms meters per second. Let's double check our work here. We have the mass of the rifle, which is 0.8 kilograms, times its velocity of negative 5 meters per second. 0.8 times negative 5 is a negative 4 kilograms meters per second. And that is the momentum of the rifle. So basically they're both 4 kilograms meters per second, but one's positive and one's negative. In other words, the bullet's going in what we assign to be the positive direction, and the rifle's going in what we assign to be the negative direction. Now you'll have several examples, real world examples from the book and so forth. Bullet being fired from a rifle, car crash, skaters rather pushing off from each other, cannon on a boat, things like that. All of which boil down to this basic idea. But if they say that the momentum is conserved, that means momentum of object going in one direction is the same as momentum of the object going in the opposite direction. And that's the understanding you need behind it.